Hey, what's going on, everybody? Mario Dealba here, CEO of Elektrik. I am so excited to show you what we're working on. And to do that, I'm going to give you a little sneak peek on our connector tool. So a lot of you are familiar with our cable configurator. What if instead of just going through the cable, you could just quickly pick if you have a crimp connector, if it's copper, if it's aluminum, or if you have a Shearbolt, and just quickly click through and find the parts and price and availability for all your parts. So on that topic, Shearbolts, I've had a ton of questions about Shearbolts lately. How do they work? Are they better than crimp connectors? So I'm going to be very, very, very honest right now. I'm not going to tell you if they're better or not. I'm going to let that be something the manufacturers tell you. But what I'm going to do is I'm just going to quickly run through how they work, the physics behind it, because a lot of people don't know, but I'm an engineer. And I actually studied this topic in college. It's called Mechanics of Materials. And I'm going to show you, oops, I'm making noise here. Here's a couple options that we actually carry. So this one's made by Tyco, by TE, Raychem. And this one is made by Pfister. And they're both Shearbolts, okay? So they both have two different technologies on how they shear the bolt, but the concepts and the physics are very, very, very similar. So to understand how a Shearbolt works, I'm actually going to use a graphic by Nexans, because I think they just do a really good job on the graphic. So here in Nexans, as you torque the bolt down, let's go just a little bit before, even more. It's bolting down. The cable is deforming and pressing up against the walls of the connector. Boom, it shears, it's connected. Really, in engineering, we would call this, it's going through elastic deformation and eventually reaches a plastic deformation, which is the point of no return. The cable is not going to bounce back. It's just going to smoosh down against the connector, and the force is so great, downward, Newton's third law, the reaction force. Every force has a reaction force. The force upward is equal or greater than the force it takes for the bolt to break off. And that's called the shear. I want to show you, this is the thumb rule, okay? Right hand thumb rule. There's the force downward, and that force downward has a shear force. It's funny because, it twists to the right, just like screws do. It's kind of cool, right? So when the force downward, which there's a reaction force equal, is greater than the force that the bolt can take, it snaps off, which is great because that force, if we can know the force that the cable needs to be properly touching the walls, we can then design a bolt that it shears at that force. So that's how Shearbolts work. The engineers are very smart, and they've designed, I'm going to pull out the bolt. They say, okay, copper, it has this density, and because it has this density, it has a modulus of elasticity that equals this much, so it requires this much force, and aluminum has this much, so this is the amount of force. So they probably designed for copper, I'm going to guess, because it's greater. So they say, okay, based on that modulus and that amount of force, here is the thickness that the bolts need to be to break off when the force of the conductor against the walls is what we need. So with that said, I'm going to show you a couple of graphics that are awesome. So here's Pfister's graphic, and it shows that two different types of conductors are matched to the inline connector, two different sizes. So copper on the left, aluminum on the right, one's greater than the other one, and regardless, you have a nice butt splice. I'm going to show you a quick video of the Raycam Shearbolts. The bolts have to be fastened in a specific order. So it's very important when you're working with Shearbolts that you pay attention to the order that you fasten the Shearbolts. See, he did the one on the outside first, tightens it enough, and now he's going to break it off. And bloop, it should come off. Yep, there you go. Comes off. Okay. So that's really it. You know, one of the benefits of, well, I think I'm going to leave that for the next video on why people would use Shearbolts versus crimp. I think for now, I think you just got enough. I'm going to add some more technical stuff to the post and to the video. But basically, here is how that phenomena, and if you wanted to calculate the thickness of the bolt, how you would do that. If it was a solid bolt, you would use the solid rod equation for your second moment of inertia, which would be like Raycam's. If you had a hollow rod, which is a hollow bolt like Pfister, you would use this formula right here. And you would calculate the thickness of the wall right here, C4 and CI. Okay. Thank you so much for listening in. And if you have any questions, happy to answer them. And go get signed up with Elektrik. Okay, see ya.